Okay, so now we're going to consider a really interesting kind of motion called rolling motion. And rolling motion is a beautiful combination of translational motion and rotational motion. Now we've talked about both of those types of motion before, and rolling motion combines them together in this beautiful way that that allows for a lot of really interesting and rich physics. Okay, so so here is a wheel, and this is the wheel rolling along the ground. Okay, now the first and most important thing to understand about rolling motion is that by rolling motion we mean rolling without slipping. This is not rolling motion because the point of contact is sliding, it's slipping relative to the ground. There's relative motion. Okay? This is also not rolling motion because the point of contact is slipping or sliding along the ground. There's relative motion between the two of them. By rolling motion, we mean that the point of contact is always momentarily at rest with respect to the ground. Okay? So rolling motion is this sort of beautiful synchronous kind of motion. It's a combination of translational motion like this without rotation, plus rotational motion without translation. If I combine the two of those together and they're synchronized with each other, then I will have the wheel rolling without slipping, rolling such that the point of contact is always momentarily at rest. You know, the point of contact is, now this one, and then now this one is in contact, now this point is in contact, and so on. That point of contact is always momentarily at rest. Okay, so to see that more clearly, I want you to notice that any point on the rim of the wheel, say this point over here, when the wheel rolls, it undergoes complicated motion. Okay, just watch it. Okay, while the wheel rolls, it's complicated motion for that point on the rim of the wheel. Okay, but the important thing to understand is that that when this point becomes the point of contact, it is momentarily at rest. So here it's moving fast, it's moving slower, 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 momentarily at rest, and then faster, faster, faster. Okay, so it's moving fast. It's moving fast, and then slower, 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 momentarily at rest, then faster, faster, faster. In fact, you can see that when the wheel is rolling, the point of contact is at rest. Points on the wheel near the point of contact are moving slowly, but the further you get away from the point of contact, the faster that point on the wheel is moving. Okay, so one way to sort of see this really clearly is to focus your attention on 3 points on the wheel. There's the point of contact, there's the center of mass, and there's the point at the top of the wheel. Okay, and so what we're going to do is we're going to sort of draw a line between those points by sticking this rigid body here. Okay, and I'm going to take this rigid body and I'm going to clamp it onto the wheel. Okay, so now notice how this rigid body, this 3 set of points, notice how they move when the wheel rolls. Okay, so I'm going to roll the wheel from this position to that position, this position to that position. And what you notice is that this rigid body, the kind of motion it undergoes is like that. Okay, so it's not rotating about its center of mass. It's rotating about the point of contact. There's an axis passing through the point of contact perpendicular to the board, and it's rotating about that axis. So rolling motion is not this. Rolling motion is this. Okay? And so the wheel is a rigid body which between this instant of time and that instant of time, this infinitesimal time interval, what it's doing is this point is fixed and it's doing that. So we have a rotation not about the center of mass, we have a rotation about the point of contact, the edge of it. Okay? That's crucial. And you can see that when the wheel is moving from here to here, so it's doing, this sort of a thing, when it's moving from here to here, then This point does not move, velocity is 0. This velocity is small. This point on the wheel has a higher velocity. This point on the wheel has a higher velocity. And the point on the wheel that's the furthest from the point of contact, the top, is moving the fastest. Okay? So, yeah. So let's try to, let's draw some diagrams and put some math to this. Okay? So we've got a wheel. And this wheel is rolling along the ground. And the point of contact, okay, the point of the rim of the wheel that's instantaneously in contact with the ground is momentarily at rest. So this is the point of contact. So POC means point of contact. And the crucial thing about the point of contact is that it is momentarily at rest. Okay, momentarily at rest. Okay, so that's that. So this is the POC. And then, of course, there's the center of mass point over here. And when that wheel is rolling, okay, the center of mass point is moving along with some velocity. Okay, and so we call that the velocity of the center of mass point. So we call that VCM. Okay, and the distance between the center of mass point and the point of contact is the radius of the wheel, r. Okay, so we have that. Now, one question that we might that we should answer here is, what is we know that as that wheel is rolling, the point of contact is momentarily at rest, and points on the wheel near the point of contact have small velocities. The center of mass has velocity VCM, and points that are further away have greater velocities. So the natural question is, what is the velocity of the point at the top of the wheel? That instantaneous velocity. So what is V top? Okay, so we're going to think a little bit about that. And we're going to think about it in the context of just singling out this point, and this point as the wheel rotates. Remember, rotation of the wheel is like that, with the point of contact momentarily at rest. Okay, so we're talking about this kind of motion. So let's draw this stick here. Okay, so we've got the stick. So this point on the stick is the point of contact. This point on the stick is the center of mass point, and this point on the wheel is on the stick is the top of the wheel. Okay, and so the idea is rolling motion is the point of contact. I've got a rigid body that's touching the ground, and it's rotating about an axis that passes through the point of contact, and it's rotating with some angular velocity. Okay, certain number of radians per second is happening there. And so let's call that omega point of contact. Okay, some number of radians per second is the instantaneous angular velocity of that rigid body about the point of contact. And then so we ask, well, what is this velocity? So if the radius of the wheel is r, so the distance from the point of contact to the center of mass point, if that distance is r, then we know that the tangential velocity of this point in that rotating rigid body, that tangential velocity is equal to the angular velocity, omega point of contact, which all points in the body have the same angular velocity, multiplied by the radial distance, the perpendicular distance from the axis of rotation. So that's r times omega point of contact. Okay? And now, a crucial thing here is we know we have to choose omega point of contact such that r times omega point of contact is the desired velocity of the center of mass of the wheel as it rolls. So we set that equal to VCM. Okay, so this is our first important result here, is that the velocity of the center of mass of the wheel as it rolls is equal to the radius of the wheel, okay, times the angular velocity of the instantaneous angular velocity of the wheel about its momentarily at rest point of contact. Okay, it's this. Great. So then we say, well, what's the velocity at the top of the wheel? Okay, well, that's easy. it's the same idea here. So the velocity, the tangential velocity of the point at the top is equal to the angular velocity of that rigid body, omega, about the axis passing through the point of contact. It's that angular velocity, omega point of contact, times the radial distance from the point of contact, which is 2 times r, because that's r plus r is 2 times r. And so the tangential velocity here, which is v top, is equal to 2r times omega point of contact. And since 1r times omega point of contact is VCM, this is twice VCM. Okay? So we have sort of the obvious result that rolling motion is this kind of motion with an angular velocity omega point of contact. And if we have a velocity VCM here, it'll be 2 VCM at the top of the wheel. Okay? So that's that. What else? Okay. So now what we're going to do is I want you to understand this is one way to think about rolling motion as an angular velocity around the point of contact. So the body doing this kind of thing, the rigid body doing this. Another way to think about it is translation plus rotation. So rolling motion like this is equal to translation without rotation plus rotation without translation. And when you combine the two of them together, they're synchronized so that it rolls without slipping. The point of contact doesn't slip. It's always momentarily at rest with respect to the ground. So rolling equals translation plus rotation. Okay, so let's just draw a picture here. So this is the picture for rolling. And rolling is basically, there's a point of contact which has a velocity 0. It's momentarily at rest. And then the center of mass point, so the object is doing this, and the center of mass point is moving with a velocity VCM to the right. And the top of the wheel, the point at the top of the wheel, is moving with exactly twice the velocity, twice VCM. Okay? So this is our picture of rolling motion, thought of as point of contact momentarily at rest. Okay? But this rolling motion is actually equal to a translational motion, translation with no rotation. Okay, so that means we have the wheel like this. It is not rotating, it is just translating with every point on the wheel moving with the same velocity VCM. No rotation, translation only. Okay, so the center point is moving with the velocity VCM, as are every other point on the wheel, including the top is a velocity VCM, and the bottom is a velocity VCM. Okay, and now the claim is that rolling is translation with no rotation plus rotation with no translation. Okay, rotation with no translation means it's doing this. The center of mass point is not moving. The velocity of the center of mass point is 0. Okay, and the wheel is rotating with some angular velocity, not now about the point of contact, but now about the center of mass. Okay, so here's our wheel. And we are saying no translation, so the velocity of the center of mass point is 0. However, this wheel is rotating about the center of mass point. Okay, and so there's some angular velocity, omega, about the center, around an axis passing through the center of mass point, some number of radians per second. Now you might guess that omega center of mass equals omega point of contact, but we'll actually prove that right now, okay? So the idea is you say, well, what we want is, we can see that if we combine the velocity, if we look at the center of mass point, in the translation with no rotation, it's moving to the right with a speed VCM. In the rotation with no translation, it's not moving. So VCM plus 0 is, if we add the two motions, VCM plus 0 is VCM. So we account for the motion of that point, the center of mass point. Let's try to account for the motion of the point on the bottom, the point of contact. Okay, so that point of contact should be at rest. In the translation picture, it's moving to the right with the speed VCM, which means in the rotation picture, it better be moving with the speed VCM to the left. Okay, so that the velocity VCM to the right from translation plus the velocity VCM to the left from rotation add to 0 because the point of contact is momentarily at rest. Okay. Now, of course, if you've got a wheel rotating around like this, and one point on the wheel has a tangential velocity, in this case VCM, then of course every point on the wheel has a tangential velocity VCM. Okay? And so then you can see, oh great, so now this also works for the top point. If you add a velocity of VCM to the right from translation plus a velocity of VCM to the right from rotation, you get a velocity of 2 VCM, which is exactly what happens in this picture of rolling motion. So this picture is equal to this plus rotation about the center of mass. Okay? That's what's happening here. Okay, now in order for this to work here, remember we had that R times omega point of contact is equal to VCM. However, we also know that if the radius of this wheel is R, and this wheel is rotating about its center of mass point, okay, with an angular velocity omega cm, then the tangential velocity of a point on the rim of the wheel, a perpendicular distance r away from the axis of rotation, will be moving with a tangential velocity of r times omega cm. We need that r times omega, we need to choose omega cm such that r times omega cm is VCM. Okay, so this is r times omega cm. Okay, so this is an important result. Very important result. So what it tells you is, well, that means, cancel the r's here, that means omega point of contact is equal to omega cm. So that's an interesting and important result. So when the wheel is rolling like this, okay, the point of contact is momentarily at rest and the wheel is doing this. It's rotating with some angular velocity about the point on the bottom, and that's omega point of contact. But also, from the point of view of someone riding along with the wheel, they say, oh, around the center of mass point, that thing's rotating with an angular velocity omega cm. What this analysis shows you is that those two angular velocities, this angular velocity and this angular velocity, are the same. Okay? And so we'll just give them a common name. We'll just call it omega. So omega point of contact is equal to omega center of mass, and we'll just call that omega, the angular velocity omega. Now, of course, that common angular velocity could be changing with time, right? So if the wheel is picking up speed, maybe it's rolling down an incline, so it's picking up speed. So both its translational velocity and its angular velocity are increasing, okay? So omega could be changing. And so the time derivative of omega, the rate at which omega is changing, is the angular acceleration. So if I take the time derivative of all three of these terms, it says that the angular acceleration, okay, so the rate at which the rotation about the point of contact is changing, is equal to the angular acceleration about the center, for rotation about the center of mass. That's this. Okay, that'll be going slow first, then faster and faster and faster as the wheel rolls faster. Those two angular accelerations are the same as well. Okay, and we'll call that, this common angular acceleration, alpha. Okay, so this is a very important result. Okay, and then the other two important results that we want to highlight, which we've already worked out. So we have, we have this here. So VCM, so let's just sort of summarize. So VCM is equal to either r times omega cm or r times omega point of contact. Well, that's just r times this common omega. So VCM is r omega. So the velocity, meters per second, of the center of mass point is equal to the radius of the wheel times the angular velocity of the wheel either about the center mass point or about the point of contact. They're the same. Okay? And the other thing is VCM, as the wheel, say, rolls down an incline, it's picking up speed, and so VCM is changing. Well, so is omega. So VCM is increasing, omega is increasing. So the time derivative of VCM is the acceleration of the center of mass point. Okay, it's going faster and faster and faster. So acceleration of center of mass point, just take the time derivative of both sides of that equation, is equal to r times the time derivative of omega, which is alpha. Okay? So that's a really important result here. Okay, we'll put 2 boxes around it. Okay? But I want to emphasize, and this is a super important point here, these two relationships are true only in rolling motion, which means by definition no slipping. Okay? So what I mean is that when a wheel is rolling so that its point of contact is not slipping, then both of these relationships are true. However, I could have this situation where you have a car, on ice and its wheels are spinning. Okay? Well, in this case, we have a non-zero omega, but we have a 0 velocity of the center of mass. That's non-zero and that's 0. So this equation doesn't apply. It doesn't apply when there's slipping. Okay? That's very important. I can't count the number of times you guys make this mistake of applying this when it's not true. Okay, so for instance, a good example is a bowling ball. Okay, so a bowling ball, you throw the bowling ball like this. Suppose the bowling ball is initially not rotating. You throw it like this, it hits the bowling alley floor, and it slides for a while. During this time, obviously, omega is 0, but VCM is not 0. So this relationship doesn't apply. But while it's sliding, there's a force of kinetic friction that the bowling alley floor exerts on the bottom of the wheel there. And so then from the point of view of someone in the center of mass, they see a force that way acting on the wheel, causing the wheel to rotate faster and faster. So it starts out with no rotation, 0 angular velocity, and it slides. The kinetic friction is increasing the angular velocity until a little ways down the bowling alley, the ball is now rolling without slipping. Okay? And then these two relationships are true. Okay? So be careful with that. Great. So we have that. Oh, and now this is really cool. So clearly, we had this sort of argument here showing that rolling motion thought of as this kind of motion with the point of contact fixed is equal to translational plus rotation about the center of mass. And we could see how all that works out. But it also works out for energy, kinetic energy, because obviously a rolling object is storing kinetic energy. It's storing energy of motion, okay, because you have masses. That mass is in motion, that mass is in motion. You've got a bunch of masses in motion, so they store kinetic energy, okay? And so it turns out, interestingly enough, that the kinetic energy associated with rolling motion is equal to the kinetic energy of this wheel translating like this, okay, with a velocity VCM, plus the kinetic energy of this wheel rotating like this. Okay? So they add up. So kinetic energy of rolling is kinetic energy of the translational part plus of the motion plus kinetic energy of the rotational part of the motion. So to see this is really a beautiful little argument here, and it makes use of the parallel axis theorem. So make sure you know that parallel axis theorem. It's a super useful thing. Okay, so kinetic energy, the kinetic energy associated with rolling, well, let's see, what does that mean? Well, what it means is at this instant of time, this point of contact is at rest, and this rigid body is rotating about the point of contact with some angular velocity omega point of contact, which is equal to our generic omega there. Okay, and so there's definitely a kinetic energy associated with this kind of rotation about the point of contact. Okay, and so what is that? Well, for rotational motion, kinetic energy is 1/2 I omega squared. So in this case, it's 1/2 the moment of inertia for rotating the wheel about the point of contact. So it's I point of contact times omega point of contact squared. Oh, but that's just omega squared. Okay, and so our picture looks something like this. We've got a rigid body like this. We're not considering its rotation with the center of mass. What we're considering is it is rotating about the point of contact with an angular velocity equal to omega point of contact, which is the same as omega. So it's doing this. Okay, and then the center of mass point is over here. And the mass of this wheel is, say, m. And so It has a mass m, and it has a moment of inertia for rotation about its center of mass, ICM. Suppose we know that, okay? And of course, the radius of the wheel is r. All right, so then what we need to do is this I point of contact is we are rotating this rigid body about an axis that is not passing through the center of mass. The center of mass is here. We are rotating it about an axis that's parallel to this to rotation about the center of mass. We're rotating it over here, okay? And so we can apply the parallel axis theorem, which says that the moment of inertia for rotating this rigid body about the end point over here, the point of contact, is equal to the moment of inertia for rotation about the center plus, that's ICM, plus imagine all of the mass of that object concentrated at the center of mass point, and it's connected by a massless rigid rod, in this case of length r, to that rotation point. Well, that moment of inertia is just that total mass of the object, m, times r squared. So we have an mr squared plus an ICM. That's what I point of contact is. Okay? So this is equal to 1/2. Let's put the mr squared first. So it's the total mass of the object concentrated at the center of mass point, m, and that center of mass point is located a perpendicular distance r from the axis that we're rotating about. So there's this contribution, mr squared, to I point of contact, plus the rotation of the object about the parallel axis passing through the center of mass, which is ICM. So plus ICM, and then that's all times omega squared. Okay? And then we say, oh, but wait a minute. We know that, so let's just write this out. Well, actually, let's do it in one last step. We know that what is r, because here we have an r squared omega squared. What is r omega? Well, r omega is just the velocity of the center of mass point. So that's just VCM. Okay? And so what we get here is we get 1/2 the mass of the wheel times VCM squared. That's the first term. The second term is 1/2 ICM times omega squared. Okay? Now you recognize this as 1/2 mVCM squared. That would be the kinetic energy associated with a wheel of mass m that is not rotating, that is translating only with a velocity VCM. Kinetic energy of translation is 1/2 mVCM squared. So this is the kinetic energy associated with the translational component of the motion. And then, of course, this second term is the kinetic energy associated with a wheel whose center of mass is at rest and it's only rotating. It's a rigid body rotating with a moment of inertia ICM rotating with an angular velocity omega cm. So that's 1/2 ICM omega cm squared. But omega cm is the same as omega. So 1/2 ICM omega squared is the kinetic energy that's stored in this rotating rigid body, rotating about its center of mass point. Okay, so this is the kinetic energy associated with the rotation. Okay, so in pictures, this is the kinetic energy associated with the wheel not rotating, but every point moving with a speed VCM. Okay, plus a wheel whose center point is at rest, but is rotating with an angular velocity omega and has a moment of inertia ICM. Okay, great. So that's really important. So we're thinking about rolling motion. It's very important you understand rolling motion from both points of view. You think of it either as a rigid body whose point of contact is momentarily at rest, and it's rotating about that point of contact with an angular velocity omega point of contact, or you think of it as translating with a velocity VCM plus rotation about the center of mass point with an angular velocity omega cm. And those two angular velocities are the same, they're just this omega. And so you get this sort of picture of rolling motion, which is really nice. And then this picture is borne out also in terms of the energy involved. The kinetic energy for rolling, that kinetic energy is equal to that kinetic energy plus that kinetic energy. So it's really nice. Okay, so now we're going to apply this to a really interesting example. All right.